We have a couple applications of vectors that we've been talking about. So check out number 8. We want to find the component form of the vector that represents the velocity of an airplane descending at a speed of 150 miles per hour at an angle 20 degrees below the horizontal. And we've got a picture here that's from the example in the book. So like we talked about on the previous page, or in the previous video, our vector, we can think of our x component as the cosine of theta and our y component as the sine of theta. So that's where these pieces come from. And then on the last video, they were unit vectors. Okay, so it was only a 1 unit long, but this one has a magnitude of 150. So we have to multiply both of those components by that magnitude of 150. So when we do that, our magnitude is 150 miles per hour. And we want to do the cosine of our angle, which they gave us is 200. Now, the I is just telling us that's the horizontal component. And then our magnitude, again, is 150. We're going to do the sine of 200. And the J is just telling us that's the vertical component. This is not a special rate triangle. It's not something that we're going to do exact value of. You're just going to go to your calculator and do 150 times cosine of 200. And your calculator is going to tell you negative 140.95. And you're going to do the same thing, 150 sine of 200, and your calculator is going to tell you negative 51.3J. And that is your answer, except it wanted component form. So we're just going to write it like this. Negative 140.95, negative 51.3. Okay, and what this is telling us is that this vector is going left, negative 141 basically, and then down negative 51. Okay. All right, this is where you may have seen vectors in physics. So we have a force of 600 pounds is required to pull the boat up a ramp. Boat and trailer, inclined at 15 degrees. Find the combined weight of the boat and trailer. Okay, so the force required is 600 pounds to get it up this ramp. Okay, now 15 degrees, so that's down here. They drew that in for you. We want to find the combined weight. You'll remember from physics that weight acts directly down, perpendicular. So we are looking for this thing right here. Okay, I'm going to call that x. Now, I'm just going to transfer this down here, that distance here. That was 600. And then this 15 degrees, that 15 degrees is using similar triangles, is right there. Okay, so what we end up with is this right triangle. And we're trying to solve for x. And so just using SOHCAHTOA, we can see that 600 is opposite, and we're trying to find hypotenuse. So we'll say that the sine of 15 degrees is opposite over hypotenuse. And then we just need to multiply both sides by x and divide both sides by sine and put that all into your calculator. 2,318 pounds. Okay, so to do these problems, you're going to see maybe one of them on your homework, but remember that weight is acting downwards, and then you're going to draw your right triangle from that. All right, number 10. This is the one you're not going to like me on. That's okay. I can deal with that. An airplane is traveling at a speed of 500 miles per hour with a bearing of 330 at a fixed altitude, and there's no wind. But then it gets to a certain point and it encounters a wind with a velocity of 70 miles per hour in a direction north, 45 degree east. What are the resultant speed and direction? Okay, let me show you what's happening here. So this V1, that's the airplane. It's just flying along, minding its own business. And then all of a sudden wind acts on it and it pushes it a little bit. That's that V2. And then that gives us this resultant vector, okay? It's pushing the airplane off course slightly. And that's what we need to find. So basically, the way we're going to approach this problem is we need to find a vector for the airplane, find a vector for the wind, and we're going to add them together. Sounds simple, right? Okay, so first we're going to find the vector of the plane. All right, so the vector of the plane, this is similar to 2 problems ago. We need to do the magnitude, 500. And then to get our x component, we have to do the cosine of its angle. Oh, but its angle. It's a bearing of 300. Let me draw this down here. But this is an airplane bearing. Okay. So remember, airplane bearings, that's not what I wanted, happen from the north, and it's going 300. Okay, that's where it's at. But we want to measure, let me get another. So this is the airplane. But we want to measure from here. Okay, so if it's 300 around here, that means this little piece of it is 60. And then if we want to measure from here, that adds another 90. So the actual angle of the airplane is, wait, nope, I did that wrong. It was 330, that's why. Oh my goodness. 330. So that was not 60. Okay. So if it's 330 here, that little part is 30 degrees. This part's 90. So the actual angle of the airplane is 120. That's what we need to put in here. Cosine 120. Our y component is our magnitude, sine of 120. And let's see, we can do, I'm trying to decide, we can do exact values for these. It'll be okay. Cosine of 120 is just negative 1/2. So this is going to give us negative 250i. Sine of 120 is root 3 over 2. So that's going to give us 250 root 3. Okay, so that is the vector of the airplane. If you want it in component form, it would be negative 250 and 250 root 3. Okay, now we need the vector for the wind. That was supposed to be a W. I don't know what happened there. All right, we're going to do the same thing. The wind has a magnitude of 70, and then we need its angle. Now, the wind should be a lot easier. Okay, so if this is the wind, it is from the north, 45 degrees east. We need this angle, which is still going to be a 45-degree angle. So theta for the wind is 45. So cosine 45, and then our y component, that was I. Our y component is 70 sine of 45j. We can do exact values of these two. Cosine of 45 is root 2 over 2, so that's going to give us 35 root 2 I. And sine of 45 is also root 2 over 2. So that will give us 35 root 2 j. So 35 root 2 and 35 root 2. Okay. Now, I think I need a little bit more space. Let me erase some of this stuff. We want to find the resultant vector. So remember, the airplane is happening and then the wind is blowing. So we basically need to add the two vectors that we've just created. Those don't want to erase. That's okay. Whatever. So our resultant, I'm going to call it our vector combined, is we're going to take the vector of the plane, negative 250, 250 root 3, plus the vector of the wind, 35 root 2, 35 root 2. So our combined vector, you can go ahead and do this in your calculator. You're going to add your x components. So negative 250 plus 35 root 2 in your calculator turns out to be negative 200.5. And you're going to add your y components. So 250 root 3 plus 35 root 2 is 482.5. So what this has shown us is this resultant vector. It's this guy right here, negative 200.5 to the left and up 482.5. Now, that is the vector, but that's not what the question was asking for. It wants to know the resultant speed and direction. Okay, so to find speed, speed is the magnitude. So we need to find the magnitude of this combined vector. So remember, that's just the distance formula. In this case, we can use that modified distance formula. So we're going to take negative 200.5 squared plus 482.5 squared. We're going to take the square root of that. We're just going to put that all into the calculator because those are big numbers. And we get 522.5 miles per hour. That is the resultant speed. So this wind, remember we started at 500 miles per hour. So having this wind has increased the speed a little bit. We also want to find the new direction. We need to find the new direction theta because we have blown the airplane off course a little bit. So to find theta, remember we're going to use this formula. The tangent of theta is b over a. Here's our b, 482.5. And a is negative 200.5. So we're going to do inverse tangent. We're going to put that into the calculator, and the calculator is going to tell us negative 67.4 degrees. But that's in the wrong quadrant, obviously. That's in the fourth quadrant. Clearly, our picture's in the second quadrant, so we're going to have to add 180 to adjust for that. And we get 112 degrees. 112.6 degrees, I'm sorry. Now, that's still not right because that's this angle. You remember how we want to do airplane bearings, right? Airplane bearings are always measured from the north. So if this whole thing is 112.6, the first thing I'm going to do is subtract 90 degrees, and I'll just get this little piece. So if I subtract 90 degrees from that, I get 22.6. That sound reasonable? Yes? I think I'm okay with that. Okay, and then for airplane bearings, I need to measure this direction. So I'm going to take 360 minus that 22.6. So my actual airplane bearing turns out to be 337 degrees, approximately. Okay, so remember originally we were going 330, now we're at 337 degrees. So this wind has blown us off course a little bit. So that is everything that we need to know with vectors so far in 8.3.